And we can move on to the next presentation by Andreas Kohler from Northstar, assessing deep learning for seismic array processing pipelines. Andreas?
Yeah, thank you. So in this presentation, I will talk about how we can use machine learning or deep learning and integrate it into seismic array processing pipelines. And the motivation is really, well, it's well known that the seismic arrays are a critical part of the IMS. So actually most of the associated arrivals come from detection on seismic arrays. There's been a lot of development. We already heard about FaceNet, for example, on single station processing using machine learning in seismology, but application to seismic arrays has not been the focus so far. So this is an overview about, like a simplified overview about the seismic processing pipeline, which is operational at the IDC, but also many other national data centers. So you start with a phase detection, then phase classification and back azimuth measurements. You associate the arrivals and finally locate them and maybe also do some event classification in the end. So traditionally, you do this on arrays with beam forming. So you create beams in different directions for different velocities, run an STR-LTR trigger on them, and then these pre-detected arrivals are analyzed further by FK analysis, for example. And then you can measure the direction and the velocity, or the parent velocity, slowness, and then from that you can get the classification into P, S waves, or other phases. So how machine learning can come into this pipeline? Well, first of all, we already heard in the phase detection phase, of course. We can use methods like FaceNet, eco-transformer, and there are many more methods out there now. And what they all have in common is that they include these convolutional neural network layers. They're organized in a so-called encoder-decoder structure. So they take the waveforms and three-component single-station waveforms as input and transfer them somehow into a detection time series for P and S waves. That's basically how they work without going into much detail. And then you can also use machine learning in the second step. So you can try to use pre-detected arrivals and use some input to do the classification and measure the back azimuth on seismic arrays. And I will show how we can do that. Finally, the event classification is also, there's also a lot of studies about that you can use also convolutional neural network layers, connect them to some dense neural network layers and do some classification tasks like, is it an explosion, is it an earthquake, for example. Well, in this talk, I will only focus on the first two steps. And more in particular, this is the methods we are using and investigating in the pipeline. We use our own version of FaceNet, which is trained on a regional data set and also like modified slightly, adding so-called transformer layers into this network without, again, not having time to go into the details. So this is a published study, actually, but originally only developed for single-station processing. But I will show in this talk how we can apply this on seismic arrays. And then we have a method we call ArrayNet, which takes basically time differences observed on an array for detected arrival and as input, and then is trained to estimate from that the back azimuth of the incoming arrival and which phase type we observe. It's basically a combined regression classification neural network. So first I will talk about the first step, the phase detection. Here we identified three different approaches how we can use these phase pickers on seismic arrays. The first one is straightforward. We call this the ensemble detection method, where we apply the phase picker on all array elements in parallel, independently, right? And then in the end, you get this detection time series for P and S waves as output and combine them somehow. And combining means basically stacking them. The second approach is to train the neural network picker directly on beams. So then you do the beams from three-component data or vertical component data, and then do the phase picking on the beams. And finally, the third approach, which we call the array detection approach, is basically where you feed the whole waveform of all array elements into the network to do the detection. So what the first, or basically the array processing is done at different steps for these three approaches. For the first one, it's done as a post-processing. For the second one, the beam detection approach, it is done as a pre-processing to create the beams. And for the last one, the array processing is directly learned by the machine learning method. The first ones can be trained on multiple arrays at the same time. So you have one single model applied to different arrays, while the third one is only trained for specific arrays. So we need an array-specific model to do that. And also the first two ones are a bit slower because you have to apply the picker on different time windows from different array elements or different beams in parallel, while the third one is only applied on time window, on one single time window including all the array stations. So now the second method, ArrayNet. I will talk a bit about what is the motivation for this method. So the conventional approach is to assume a plane wave traveling over the array, and that the back azimuth is identical to the source direction. And then you can fit the plane wave or do some plane wave fitting, basically do FK analysis or use some other methods like PMCC. And then you use a fixed velocity threshold to decide if this is a P wave or an S wave or more teleseismic phases, regional phases, and so on. The limitations with this approach is that we know that there are inhomogeneities below the array, which affect plane wave assumption. Also, you have back azimuth deviations, systematic lack of waveform coherency, and also the velocity thresholds varies between the arrays. And there are, of course, methods to deal with this, like empirical slowness corrections. But what we suggest is to use a neural network approach to do that. So which takes as an input, basically, these phase differences observed between all the array stations. This is shown in this upper plot there. So these basically time differences or phase differences in the frequency domain. And these are used to train a neural network to classify the phase type and to estimate the back azimuth. And the advantage with this is that you don't need a plane wave assumption, actually. You just learn from observed labeled data. And that's also a bit faster than FK analysis because you don't have to do a grid search in the slowness space. So we train all this method with a regional data set of events in Scandinavia, Northern Europe, and the European Arctic. So regional events. We're not going to teleseismic distances yet. And we use the data using IMS arrays, the ARCIS, Spitz, and the Finis array for that. So first, now I will go into some results for the phase detection step. And how I do that, I show these curves here, which are the so-called recall precision curves, which is a kind of metric to evaluate the performance of a phase picker. We want to have a high recall. That means we don't want to miss real arrivals. But at the same time, we also want to have a low false alarm rate, so a high precision. So to have a good performance, we want to have a point in the upper right corner, basically. And we compute these metrics for different detection thresholds, and that's why we get this curve. And what you see here is the performance curve for P and S waves for single-station machine learning phase picker. Yes, and this is done on the test data set, which was not used for training the models. In addition, we also want to test this in more operational settings on continuous data, because that's really how we see if the model performs well, not just on test data, which just includes events. So here we applied on 4 days of continuous data with hand-picked events in this case, only on the ARCIS array, but we also have results for the other array. And what you see here in addition, the black dots, this is the performance of the operational classic array processing on the ARCIS array at NORSA. So that's our baseline, basically. Now I will add these performance curves for these 3 different approaches I introduced, the ensemble detection approach, the beam detection approach using either only vertical component or 3 components, and using the whole array as input. And you see that, first of all, for the continuous data, these all outperform the S-wave detection, which is first a nice observation. And also some of them outperform the P-wave detection. And when you compare this, and all of them outperform the single station detection method, which is kind of expected when you use more stations than just a single station. On the test data, you also see an improvement, which is mainly visible for these beam detection approaches. So this is maybe a bit more intuitive example how this method works. This is just one event, an example, how these methods perform on this one. So you see very weak regional events observed on the ARCIS array. You see the individual array channels, then you see the beams, and then on the bottom you see the detection time series for P and S waves using two of these models, just for to make it a bit simpler. The array detection and the single station method. And you see, nicely see that you can even pick up this small, very weak SN wave, which you would not see in a single station processing. Now, switching gears a bit, now I'm going to the second method, and also this will show some results, but only one slide, and then I'm already close to the conclusions. So how we present the results for this method is a so-called confusion matrix, basically where you see the predicted label for given arrival and the true label. In this case, you see it for P, S wave, and also a noise class. And we want to have blue colors in the middle, on the diagonal, to have good results. And we have that. And actually, we also compared this with the operational pipeline, with that K-analysis, and we saw some improvements. It actually also improves for, if you look more like trying to classify PN with PG, SN with SG, so the regional phases. Also, this works quite well with this method. And most importantly, when you look at the back-asymptote residual obtained from classic array processing using FK analysis and this new method ArrayNet, you see that we improved we have a lower spread, so the lower residuals, and also remove a bias in the azimuth, which comes from systematic derivations of the back-asymptote with respect to the true source. So that's encouraging results, and we also have a paper introducing this method out. So this brings me to the conclusion. So we have started to develop machine learning methods and integrate them into the seismic array processing pipeline using phase pickers on arrays and also using the phase classification using machine learning. And now we are looking into how we can combine, or how we can evaluate the combined performance of both methods in the pipeline processing to come a bit closer to putting this actually in an operational, into operation. Yeah. So thank you very much.
Thanks very much, Andreas. Very impressive results. Are there any questions from the audience?
As you work with deep learning, do you see that you are blind for untypical signals, for coming from untypical back-azimuth, for example?
Yeah, that's a good point. So for if we train, for example, the phase classification, then we have unbalanced data set because we train on real data. But for this ArrayNet method, actually we can add or augment the training data set with kind of synthetic events to take this into account. In that way, like simulating events in particular directions. And I looked a bit into some events which are like events which we don't want to miss, which are maybe not so often occurring. Yes, but if there's an event in an area which is not active at all, yeah, we have to look a bit deeper into that, how it performs. But in general, I think it is quite generalized over different areas. So I think it works well to also pick up events which are not that common.
Okay, thank you.
Thank you very much. So have you applied this method to other seismic AMS array?
Yeah, so we applied it to others. Okay, so we applied it to
Yes.
ARCIS, Finis, and Spitz,
Yeah.
the phase picker. The phase classification ArrayNet, we also applied to 3 other IMS arrays. I think it was Makanchi array, Texa array, and Garus array, I think, yeah. I think there was one more. But yeah, we did the test on this. So we trained the model on these arrays using arrivals from the LEB. And also saw that basically that it
So
works.
you observe the same performances?
Yeah, similar performances.
Okay.
Yeah. I don't have the numbers right here, but yeah.
So you don't necessarily need some 3 components array? right? Mackenzie, for example.
Yes, yeah, I didn't mention that actually. So ArrayNet, they only use vertical component.
Okay.
The face picker can also use the 3 components, yeah. But the ArrayNet, the face is based on vertical component data.
Thank you very much. Very impressive.
Thank you very much. Let's thank our speaker once again.